Alrighty, 27.29. So, 150 volt battery, kablam, is connected across two parallel metal plates with an area of 28.5 centimeters squared and a separation of 8.20 millimeters. Notice this is not drawn to scale. A beam of alpha particles with a charge of plus 2e and a mass of 6.64 times 10 to the minus 27 kilograms is accelerated from rest through a potential difference of 1.75 kilovolts and then enters this region between the plates perpendicular to the electric field. What magnitude and direction of a magnetic field do we need to introduce to keep the alpha particles from being deflected between the plates? So first things first, let's figure out what we're starting with. We know that we're starting from rest and being accelerated through a potential. So how fast is this little dude going? So, to begin, this is going to be a conservation of energy problem. So, we are being accelerated by a potential, so we have some potential energy, and then we're converting all of that into some kinetic energy. Potential energy that you get from a potential is equal to Q times the voltage. So, the speed that our little dudes are going when they enter the plate is 2Q, the voltage, over M square rooted. So it's 2. Their charge is 2 times E, so that's 2 times 1.602 times 10 to the minus 19 coulombs. That potential was 1.75. That is not a 5, that is a 7. 1.75 kilovolts, so that's 10 to the 3 volts. Their mass was 6.64 times 10 to the minus 27 kilograms. So I stuff this into our handy dandy calculator that doesn't belong to me. 1.602 times 10 to the minus 19. That is not a 19. There we go. Times 1.75 times 10 to the 3. Divided by 0.64 times 10 to the minus 27. Square root of that is. So the speed that they're going is 4.12 times 10 to the 5 meters per second. Okay, so now we have some particles zooming in here. In order to get all the way through without being deflected, we need the net force on these guys to be equal to 0. So if I have a bunch of little positive particles coming in here into this electric field, they're going to start feeling a force along the direction of the field. So they're going to start going like that. That's all we want. So we need to have a magnetic force that's going to cancel this out. So, cancel forces. So the force from the electric field is going to be Q times the electric field. And that has to be equal to the force from the magnetic field, which is QV cross B. So the charge doesn't actually matter here. So E equals V cross B. Okay. So let's right hand rule this thing. The force from the electric field is going to be going this way. So to cancel it out, we need the force in the magnetic field to be going this way. So I bust out my right hand rule. My F equals QV cross B. So I'm going to put my F in the direction I need it to go. My QV in the direction my positive particles are moving. So my B is coming out of the page. So QV cross B gives me a force going up. That's way. So my B has to be coming out of the page. Okay, so now B and V are perpendicular. So we can just say that's V times B. The electric field between these plates, they give us the voltage and they give us the distance between them. So if you remember, what was it? Electric field times the distance equals the voltage. Yeah. Volts per meter times meters equals volts. So this, I'm going to write E as voltage over distance equals velocity times magnetic field. So my magnetic field is voltage over distance velocity. So my voltage of my battery is 150 volts. The distance between them is 8.2 millimeters. And my dudes are traveling at 4.12 times 10 to the 5 meters per second. So if I punch that into my handy dandy calculator, 8.2 times 10 to the minus 3 times 4.12 times 10 to the positive 5. My magnetic field is going to be 44.4 millitesla going out of the page. Huzzah! We did it!